Hi everyone. Today I'm going to present the second presentations in petrophysical series of presentations. It will be done bi-weekly as I promise when I have time for that. Last presentations we have presented the gamma ray and applications, and I hope you guys get some benefit out of that. Today actually I'm going to focus on the petrophysical interpretations in terms of porosity analysis. So the outline of presentation today will be porosity definitions, what is the reservoir rock contents, different types of porosity in clastic and carbonate, atom structures. Yes, sure, we'll go to the atomic structures. Later on you will know why. Neutron physics, neutron corrections, density principle and porosity from density, and the application for that, and the combination between this and neutron application about that. So first of all, everybody knows about these simple Archie equations, which is actually is the equation to calculate the saturations of water, and later on 1 minus saturation of water gives the saturation of hydrocarbon. You can see the RW, A, M, and N. All this later on in separate presentation. I will cover this kind of equations and how to do that. But now let us see this parameter here. We are focusing on this parameter today. From 2 towards dense and neutral, which is actually the porosity. So without the porosity, you cannot actually get the hydrocarbon, saturation of water and the saturation of hydrocarbon. Also, you cannot get the volumetric analysis, you cannot get your modeling, because the geologist using for modeling distributions and all these kind of things. That means it is very important. So we have to know first what is the porosity, what's the definition, what type of porosity, how can I determine the porosity from the dense neutron in our presentation. We'll focus for that, and what is the applications, and we'll see some real cases in the real data or from different places. So what is the porosity definitions? Porosity definition is very simple. It's just the void space divided by bulk volume. It's a ratio between void space divided by bulk volume. So what is the void space? Is the bulk volume minus matrix volume, and it divided by the bulk volume. So let us see one example, just a very simple example indicating this kind of equations. So imagine we have a core sample. It's a length 12 centimeters, and the diameter is 4 centimeters. So this kind of this core sample, it's already when it's dried in the lab, and we found that the weight is like 4 to 5. After that, we saturated to 100% water, and we found the weight 453. Specific gravity for this parameter is 1.07, and the length 12 centimeters, and the diameter is like 4 centimeters. So how can you apply this equation to get the porosity for this core sample? So it is very simple. First of all, we have to get the bulk volume, which is like, actually this is a cylinder, should be by R square time L. This is the depth. And after that, we'll get the void space, which is actually the pore volume first, which is like the weight of the sample with the water minus the weight of the dried divided by specific gravity, and divide both the pore volume divided the bulk volume, will get actually the porosity. And you can see the calculation. It is very simply indicated this kind of calculations. So this cartoon here showing actually the matrix and the porosity, void space in this case. We have to look, actually here is very important things we need to emphasize here. This kind of pore here is called pore body, and here is called actually the pore throat. The pore throat, actually it is very important for permeability, and the pore body is related to the porosity in this case. If you have a pore body very big, but there's no pore throat and the connectivity between this kind of pore space between the grains, that means it's useless rock. You cannot call it reservoir rock. That means you have a high porosity, but there is no permeability. So permeability is very important part in this case. This is in cartoons after we fill it with the oil and water, okay? In this case oil, and also you can fill it with the gas. If you can see here, this is a grain density, okay, and this is actually the connate water or indivisible water in this case. And this is actually the unwetting phase, which is actually in this case might be oil, might be water. But in this is actually it is oil, okay? That means this is our rock reservoir with the fluid inside. That means if we calculate how much the void space in this case, that means we are calculating the porosity. Later on, we know this kind of oil and water, it has a hydrogen index related to this kind of porosity. Once we calculate or estimate the hydrogen index in a direct way, in this case we estimate the porosity. Later on we'll explain that. So to classify the porosity in terms of classifications in the oil industry, we find two types of a primary porosity and secondary porosity. The primary porosity is actually developed at the deposition first. During the deposition of the sedimentation, it's already that times, and they can be typified by intergranulars or interparticle sandstone, for example, or intercrystallines or oolitic in the carbonate, all this kind of primary. And it's usually actually it's uniform than the induced. So you have to keep in your mind the primary porosity, it happened during the depositions. The secondary porosity actually is coming after the deposition has happened, so some development biological process occurring after that, maybe deromatizations, maybe some tectonic stuff like that, like actually fractures or vacuums. This is a two type of in the secondary porosity. You see, this is a fractures reservoir, and this actually is a void space in this case. It's like vagus. If this vagus is connected, it will be okay. If it's insulated, that means it will not contribute to production. Should be actually is not good. It's useless in this case. You will actually hear about two terminology in terms of porosity. Something called like total porosity and something called effective porosity. The total porosity is like a total pore volume divided by bulk volume. That means this kind of pore volume, as I mentioned, may be connected or not connected. If it's not connected and they're connected together, it means it's already like a total. But if this kind of pore space connected to each other, that means it's effective. So the effective porosity is interconnected pore space divided by bulk volume in this case. And here, this is example here. If you go at the bottom, you see this kind of grain, this kind of fluid. You see this actually looks like all is very interconnected between each other, which is very good. That means it's actually, you can call it effective porosity in this case. What relationship between effective porosity and the total porosity? The effective porosity actually it is the total porosity minus volume of shale times the porosity of the shale. You can call it porosity of the shale. You can take it from the log in the front of the big thick shale, and the volume of shale can actually easily determine from the gamma ray as we explained in the previous analysis, or you can get also from the neutron, from the densities and the equation for that as well. What is the total porosity? Total porosity, simplify, can do it like a porosity of the water, porosity of hydrocarbon, porosity of the bound fluid in the rock itself. So, if you remember previously, you see oil and water and the connate water. Summation of porosity for this is actually give you the total porosity in this case about that. Let's go for carbonate to give some hints about the porosity type in this. The carbonate actual porosity is very heterogeneous, and you can classify it in many things in this case. First of all, this one is an interparticle porosity. Each grain is separated, given similar pore space. You can really like grain separated each other. Okay. Intergranular porosity. A pore space is created inside individual grain. You see the grains itself, and you have some porosity has been embedded in the top of that. Intercrystalline porosity produced by spaces between carbonate crystals. This kind of crystals between them actually like that. Body porosity I have seen it actually quite before in some reservoirs. This pore is created by dissolution of shell. You see the shell of the fossil itself. You can find some sort of dissolution here in this case due to some interaction there. For fracture porosity and the channel porosity and the values in this case, you can find it like a secondary, the porosity in this case. For fracture, actually, this kind of fracture in the rock itself like that, so you can see it is like a lot of fractures, and sometimes the contribution of production coming from this kind of fractures. For the channel porosity, you see like a fracture but a little bit bigger in the sides. Vagues in this case created by the solution, so fragment but unconnected. Unconnected means it's this kind of void space, there's no any connectivity between both. To me, this is useless for the production in this case. Okay, this slide is actually what I need to show you. It's like effect of the grain size and the backing on the porosity. You know, in a rock, it has consists of, especially in plastic, of some grains. These grain size, if very well sorted, in this case actually, you have the same side. The backing, different backing methodology, it will be actually affect the porosity in this case. For example, here you see this is actually cubic backing. You see the same kind of grain size, but it's cubic backing. The maximum porosity actually for 7.7, it's almost 48% PU porosity in this case. If you have the same amount of grain size and you already did some rhombic backing, is the backing will be different? That means the porosity will be decreased in this case. It will be 27. If you have like the same backing in this one, but in the front of this void space replaced by small grains, in this case, also to decrease the porosity. That means you are blocking, like it's perceptually, you are blocking the porosity in this case. So it's also effect. But something also very important you have to know about it is the grain size actually. So even big or small, but you have sort of backing. In this case, you might not have a different porosity. You might have same porosity. For example, here this look actually made of small grains. These are small, big grains, but both of them has the same backing, and in this case, actually, you will see both of them in the same porosity, not have different porosity. So the porosity change here due to the backing, not due to the grain size in this case. I will show example, explain this point in the second slides. If you can see here, this example A, sample A, and the sample B. For the sample A, actually, you have the cubic volume is like 0.6 meter, and the grain volume actually is 0.4 millimeter in this case. If you need to calculate this kind of porosity, like 0.6 minus 0.4 divided by 0.6, you will see 33.01%. If we decrease this kind of sample and the volume is 0.3, and also here the 0.3 as a grain size 0.2, and if you see the same equation, you will see actually it is getting the same porosity amount. That means the grain size doesn't affect the amount of porosity in terms of you have the same grain size identical like that for very well sorted or rounded like that. But in the reality, you might not find this kind of grain size. And here actually again just sort of difference between backing between both porosity have the same grains. You see like 47 in the cubic backing, and rhombic backing will be like a porosity like 26 porosity in this case. So the backing is very important to affect the value porosity, not the grain size. That is the conclusion out of that. Okay, so before going to neutron and density physics and the calculation of porosity, let's first come back to the physics in the ice cores. You have to see actually the atomic structure. What is the atom structure in this case? So if you see the atom structure, and this is the periodic table in the bottom section here. Okay, any atom actual structure consists of nucleus. Nucleus actually consists of proton, which is a positive charge, and the neutron, which is like no charge, zero charge. And we have actually some electrons, which is like a negative charge, is around the nucleus in the shells or orbits around it like that. Okay? Let's see some definition about the atomic number and the atomic mass and the related charge. The atomic number actually, it is a number of protons. This is a number of proton in this case, which is actually this kind of red small circles with the proton, which is a positive charge. That means if you have like atom like 16 protons, that means the atomic number is 16. If you have like atom number is 1, that means the atomic number is 1. Okay, what is the atomic mass? Atomic mass or atomic weight is the number of protons plus the number of neutrons both together. So the neutrons and the proton both together, the summation of them, it will be actually the number of atomic mass. Okay, the net charge actually is like how the proton and the electron balance out. For example, if like I have like 5 protons and have like 4 electrons, that means you have a positive charge, net positive charge proton. If like 5 electrons and 4 protons, you have a minus a charge, minus 1 charge as an electron in this case. So some information you have to know about it for the neutron. The neutron actually have a mass of 1.67 10 bar minus 24 as a gram. This is the mass of the neutrons, very minor actually, very small amount of mass. And you have to know also the protons, which is a positive charge, is equal 1836 massive than electron. That means the proton is higher than the massive of the electron by this amount. Okay, here actually is a periodic tables. If you can see, it's subdivided to metals and metals and the noble gases and stuff like that. You can see the hydrogen in the top left list of this group, and this actually is called the group, like 18 groups and 8 and 7 actually a period in this case. So the hydrogen actually is on top of that, is actually it's very small and lighter elements in these ones. And you can see some magnesium like under metallic, aluminum under metallic, and hydrogen. All this actually later on when you see it in the chemical composition of clay, it's a metallic. That means give you very actually row resistive. That's why you imagine why the shale or clay have a resistive flow due to things, the metallic elements and the water in the bond flows. Okay, let's now focus on the hydrogen atoms. Why is hydrogen atoms? Because later on we are going to calculate the hydrogen index from the neutron tones. So the hydrogen atom actually it has only one proton positive charge and one electron here. It doesn't have any neutron inside. But also you have to keep in mind the hydrogen, okay, has the same amount of the neutrons, very close to each other. So you have to keep in mind in that. And because the physics behind the neutron later on is dependent upon these informations. So the conclusion out of that, the atomic structure is that it has like proton and electrons, okay, and the neutron. The proton and the neutron is called nucleus. It's the core of the atom, and the electron is already moving around in the circular orbit and very high speed around in the shells or orbits around the nucleus of the atom. Okay, so the neutron and hydrogen index. So if you imagine in the porous space, what is actually in terms of porous space? Porous space has a fluid. Yeah, what is this fluid? It might have water, it might have oil, it might have a gas. Yes, yes, is right. So water and oil both of them has hydrogen. This is a molecule of water have H2O, that means you have hydrogen, and is the chain of structure of the oil, it will have also H, which will like a hydrogen. That means but the gas actually doesn't have a hydrogen in this case. So let's focus on oil and water if it's inside the formations. That means if we found amount of hydrogen inside the porous space, that means it can be translated to porosity easily in this case. And this is actually what is the neutron do. It's already measuring how much hydrogen index inside the rock formations, and it translated to the porosity. But the gas doesn't have hydrogen index, that's why the porosity is coming from the gas, neutron porosity coming from the gas. It is not right, it's apparent, and this not have to be corrected. Later on, we'll touch about this. So the idea from this slide is you have to know the hydrogen index, which is actually the number of hydrogen per unit volume in this case. If you have more hydrogen in hydrogen index, that means you will have more hydrocarbon and more porosity in this case. And also sometimes also the hydrogen you will find in the water. But the idea is more hydrogen index, more porosity. Now let's come back to our main presentations, which is to cover the neutron and the density porosity. The previous slide was introduction for the porosity types, porosity, what's exactly different porosity type in terms of primary, secondary, grain size effect of the porosity, and all this kind of presentation. Now let's go to for neutron. Neutron, it's very simple. So what actually it does, very simple. We have a tools, it will be actually emit or create a neutron in the first case. It's coming from the neutron as a chemical source or chemical interaction in this case, and they will get actually a neutron out of this chemical interaction with this high energy 5.7 million electron volt. This first neutron will interact with the hydrogen inside the formations, and in this case will lose a lot of energy because the neutron actually has the same hydrogen, same mass like hydrogen, and the number of electron already has been left will be detected to the detectors. Everybody, he said, why are you using the neutron? Why didn't you use a gamma ray or use a beta or gamma or other stuff like that? Actually, the neutron and the gamma ray also both of them, because I will use the gamma ray later on for the density. The neutron has actually it's very high energy and it's very have a good ability to penetrate the media and the formation, and after that come back to be detected. That's why I use a neutron in this case. So it's again it's very easy. This slide summarize what will be happening. This is source of neutron interaction from the chemical source. It will be emit from here, interact with the formation. In this case, it will interact with the hydrogen in the formation, and after that back to near and for detector to be detected in this case. As I mentioned to you, more hydrogen index in this case will be high porosity, but it will be less count. Less hydrogen index, less porosity, high count. Why is the count rate? It's already opposite the number of hydrogen index, because what we are counting? We are counting the neutron coming back after the collide with the hydrogens. That means if you have like more hydrogen, that means the number of neutrons already emitted from the formation it will be die, so it will be less count, because the rest of the neutron need to be count. After die, the rest of the not die it will be count. In this case, actually, it is a number of that's why I get less count in high porosity and more count in less porosity, because it doesn't have too much hydrogen there. This slide actually it's showing you the life of the neutron during the interaction. So we have actually, as I mentioned, we have very high neutron, fast neutrons. It started from somewhere here, and when it interact with the formation, it will actually lose some energy and will be come to the epithermal level, will act more in the formation and will reach to the thermal level. When they interact with the formation, will lose all his energy in this case, and the captures here. In the captures, this is another tool to do that. Here in the thermal level, there is some tool to do that, and here is approximately like epithermal level, some tool to do that. Actually, in our process, like thermal tools, it will be captured, it will be count the neutron in this level, in this case, was 0.025. And this is actually the CNT tool. Okay, some other people will use APS tool, which is like epithermal level, because sometimes some elements inside the formation, such as chlorine, and stuff like that, it's already captures there. It have like very high hungry to eat the neutrons, captures the neutron. That's why it will affect the measurement in this case. That's why we use APS tool, because it will actually count the neutron before reaching to the thermal level and be captured. So they're using like that. The example for this APS tool, which number here, and this one, CNLA tools. Okay. For thermometer parameters, just to give you hints about the vertical resolutions and the depth investigation. So for the standard Neutron 24 inch, which is like a 2 feet two vertical resolutions, but sometimes they do some sort called alpha processing and enhance this kind of vertical resolution, and it came with 1 feet. Depth investigation from 9 to 12 inch is actually more deeper than the density tool. This is just some example showing you how much the porosity from different elements. Okay, as I mentioned before, all the tools is already during the manufacturing has been put in certain conditions. So that means if you are measuring same conditions, you will get the same result. If you are a different condition, you will get different result. That's why we didn't have actually ideal condition like in the lab or the warehouse during the calibration. So that's why we do a sort of correction. Unfortunately, the Neutron have a lot of corrections. Like borehole size, mud cake, borehole salinity, mud weight, temperatures, pressure, all this, and formation salinity in this case. And also if you have encasing in the casing, you have to correct it for the casing and the cement value like that. So the most important one here actually, this actually some of them are done in the during the acquisitions, and some of them done in the processing center when do the analysis. That's why I would recommend all of the petrophysicist people, please, before you do the correction for that, you have to look to the header coming from the field and what is the notes which is already the field engineer has been done. Did he hit a mud weight, did he hit the temperature, did he hit the pressure like that? If not, you have to do the rest of the correction, otherwise it will be double corrections. The most important one, which is I found it, here actually, is the temperature correction. Temperature correction is very important, especially in the deep water and the high pressure, high temperature wells, because this will affect huge effect for the Neutron in this case. So please, guys, when you do this, you actually ask the surface company to do the temperature correction. I was actually was operator company before, and unfortunately, when I looked to the logs, I found it doesn't actually do the correction for temperature. So I asked the client, ask the surface company to do it from now on. Before my joining the company, I found a lot of logs before I joined, it was not corrected. So please, this is very important to do it, because I will show an example actually to show the effect with them. Okay, here's an example for the effect of temperature on the neutron. You see, this is actually dense neutron separation, and this is temperature curve here. You can see it's big separation here, which is indication for the gas. But unfortunately, this is not the gas. Once it is a correction for the temperature, you will see both of them, it's overlay here. That means there's no gas anymore in this case. Okay, everybody can say, okay, I can see the gas from the resistivity, I can see from other looks, but sometimes if you have like a tight rock, something give you high resistivity also. But please always look for the corrections. And guys, this is very important message from my side here. Please ever don't go to do any physical analysis before you do the correction for all the logs. The first step to do the analysis is the environmental correction for the log, and to do the proper corrections in the logs, you have to see actually the header, log header in this case, and see how much the correction has been done from the field engineer, and after that you apply to overcome the double correction in this case. Okay, so now we finish actually the neutron porosity and this calculation. Now let's go to for the another very important tool, which is actually the density log. The density log, it's okay. Just to wrap about the neutron, we emit neutron, and the neutron interact with the hydrogen inside the formations. But in the density is different. Density will actually emit or creating the gamma ray. The gamma ray will interact with the electrons inside the formation. It will already interact with the formation, but it will actually interact with the electron inside the formation. This electron actually, if you remember the atom structure, is the electron inside the formation, and after that, it will count the number of the gamma ray inside this kind of detector here. So that's why actually you have to back to the physics. You have to back to the physics about that. The relationship between actually between the electron density and the atomic weight and atomic number. This is a relationship, which is rho is to z divided by a, rho b to this one. We found z divided by a in most of the element is equal 0.5 except for the hydrogen. So it will work for everything except for the hydrogen. Okay, so that's why actually for the hydrogen, because the hydrogen already filled with water and the oil, that's why we need something to be calibrated to reflect this kind of process. So that's why we make the tool calibrations actually for the water, 100% water and limestone matrix, and found this kind of algorithm relationship between the electron density and between the bulk or apparent bulk density in this case, which is this relationship. This is just a table, a very important table to show you actually what is the atomic weight, atomic number for each element inside the rock, which already always found in the oil and the gas reservoir, and the BIF and the bulk density, and the U. U is actually the rho multiplied by BIF to get the this kind of fuel. It's like photoelectric effect, it's captured like that. Again, just as the density parameter, like what we have done for the Neutron, standard like 18. The enhanced vertical resolution is actually, you can see it is less. That means its density is more vertical resolution. So you can take this as the bits is less than the neutrons, more than the neutrons, because the 6, the other one is like 12. But the depth of distribution here is a little bit shallower, not like a neutron. And this is actually, this is the matrix value for the limestone, which actually doesn't have any porosity. For limestone, zero porosity, you can see all zero porosity, 2.71, 265, 285. This is very important because you need to use it later on when you use these calculations in the porosity density from porosity. Again, like any tools, it has to be corrected. The most important correction here is the big wash out in this one and the rugosity. But the mud kick, if you have a mud kick, it's already done automatically in the tool by correction in the tool itself. So let's go to the very important part, which is like interpretation and the combinability between dense and neutron compatible scale and how it helps us to identify the lithology and the float timing. So for interpretation, the density tool is extremely useful for all this. So how can we use it actually density tool? We can use it for porosity. We'll show coming slide how to use the porosity. Lithology by combination with neutron tools. Mechanical properties, this is actually how it looks. If you see this kind of Poisson ratio, shear modulus, swing modulus, bulk modulus, and I will cover this actually in acoustic presentations, you can see all this equation independent only for compression and shear and the raw bulk. That means the raw bulk is very important inputs. So without density log, you cannot do any actually mechanical property in this case, and also the shear later on. So for geophysics, also you can also the acoustic impedance. Use it for the acoustic impedance for the seismic to get this reflection stuff. For the gas identification by combination with the neutron, you can see actually the big separation between this neutrons compatible scale. You can identify the gas. Actually, there is a lot of client rely on the density in terms of I can see Shell doing that, Petronas doing that. They're using the density and the density mode to get this kind of porosity analysis. So it has to be corrected very well. It has to be log depths matched and used properly as a log matrix and log floats to get the right porosity in this case. So density porosity calculations, as I mentioned, one of the main important parameters for those calculations is the porosity from the density. And you can see the density actually here is raw matrix minus raw bulk, which is actually from the log, divided by raw matrix minus raw flow. For simple calculations, the raw matrix is here, 2.61 if you are limestone pure. If you are actually, you know actually what is the float inside the mud, inside the flushed zone, because you know it's very depth investigation, it's very shallow. That means you're already reading in the very flushed zone, that means you know this value. Okay, for the gas reservoirs, actually, you can see the raw flows. This is a relationship between 600 mF and actually the raw matrix. Okay, this raw matrix is a very important point to get it. Actually, get it from the core. You see from the core interval. You see how much is the grain density from the core lab analysis, and you take average out of that. If you have not, you can go to also from the ECS tool. ECS tool will also make another presentation for that. It actually gives you the continuous grain density curve from bottom to top, so you can use it. And if you know the volumes, or continuous volumes, by using the density from sure you can the sum of both of them. You can get that. For this one, raw float is XO. You can actually it doesn't come automatically. You have to use actually you can use a neutron or RXO to do that. Okay, let's go to a very important part here, which is how we use both density and the neutron as a compatible scale and do the analysis. Okay, everybody knows the manufacturing, the neutron tools has been manufactured for limestone and water as a calibrations. So calibrated for limestone and water, fresh water 100%. So in this case, this is a very famous scale. It's like minus 0.15 to 0.55. You can use actually the limestone scale 1.95 to 2.5 or sandstone scale 1.9 to 2.9. Okay, some people use actually also here actually you can use 0 to 0.6. In this case, you can use actually 1.7 to 2.71 as the limestone in this case. Why putting this scale here? This is one example here. You see the scale here 2.95 to 1.5 and minus 0.15 to 1.5. I can see actually here this kind of scale, it looks like is a carbonate. Why the carbonate? Also very important point actually, guys, to differentiate between a carbonate and the limestone. It's very easy from gamma ray. Actually, the gamma ray carbonate always found it like smooth, very straight like that, no big change like this. But in the clastic, we'll see the gamma ray like that, thick shell and thick sandstone. So this looks like, actually to me, it's like a carbonate. And you can see here actually this kind of separation. It looks like I have a limestone, okay, with water, with hydrocarbon. Why is that? Because I have a porosity and I have high resistivity. That means you have already a limestone and you have hydrocarbon in this case, because there is a separation. What separation? So some people actually, you might say, okay, this separation is a sand separation due to this. No, please don't look for that. First of all, before doing that, put your limestone compatible scale and look at gamma ray to see exactly which environment you are. If you are a carbonate environment or if a clastic environment. And look for the BIF. BIF also is very important. If you have like a 5, you are limestone. If you have like not more than 2, you are in sandstone. Looks like you already here actually are in limestone with hydrocarbon in this case. Okay, another important outputs from the density is called photoelectric effect. Actually, we can get it when in the low energy gamma ray come into the detectors. We apply this kind of window to get the photoelectric effect. The photoelectric effect is very important for lithology indicator. Actually, the vertical resolution is 4 inch, and this is the value for limestone is 5, and the sandstone is 1.8, dolomite 3. So the 3 for dolomite is very obvious. The only guy have 3. It should be easy to identify the dolomite. But the limestone and anhydrite, it's very close. So how can you differentiate both? You have to see the resistivity. You have to see actually the value for the density, because the density for anhydrite 2.9 something, what's for limestone 2.71. It's very important. Some people also use a photoelectric effect to actually, especially in the heavy mud, to differentiate or to estimate the fractures. Because if you have a very good hole and have very abrupt change in the BIF, you can actually indication for the fracture, especially if you have like heavy weight. Very important point you have to keep in mind. You have to look to the mud content for the BIF. And if the BIF is very high value and they have a parate in the mud, that means it's not. The BIF is very affected and be useless. To be crazy. In this case, don't use it. You can be estimated by different like neural network to estimate it from other logs as an estimation curve. One of the important also plots called MN plot. Actually use the acoustics and the ρ b and the n-phi. Why I already presented here, because it has both n-phi neutron and ρ b to get the MN value. And actually you can use it to differentiate to get the lithology from this one, especially if you have a BIF has been affected. So if you have a BIF is affected with some heavy mud or parate, you can use MN plot in this case. Another example here, and you can see very obvious, as I mentioned to you before, you look at the gamma ray. The gamma ray, you see it's high, low, not straight like or very smooth like a curve. That means it's a clastic. This is a clastic. And you can see very obvious clay in this case here. You see this is a gamma ray. This is SP, this is a caliper in this case. This is a caliper is very engaged, just maybe it's a good condition hole. And this is the resistivity. The different some distribution for lateral log is actually shown from Schlumberger. You see, so in the shale places, all of them is overlay. Why is that? Because there is no any invasion in the shale. In addition to that, they give you low value here, low value compared to hydrocarbon, because it has a metallic stuff, material such as aluminum on the other, and in addition to have water in this case. So, and this actually looks like a potential zone. You see here very high value of neutron, and you see the density neutron separation for the, here actually the limestone. You see the separation, and this is sandstone scale. Because you have a sandstone, that means separation is getting less. But if a limestone, the separation is getting high. That means actually to me, when you get and make a cross plot for density and neutron in this case, this kind of the green here is high. Is already relying in this case, which actually looks like sandstone hydrocarbon oil in this case. By doing actually the DST is already showing oil and also very good API. And you see this kind of shale which is already bounded on this area, this area. So the shale in this case is relying in this area, but hydrocarbon is area. One important thing is you have to keep in mind, guys, in this kind of cross plot. First of all, you can see this actually is make a general for all environment, like for sandstone, limestone, dolomite. That's why I always say from the beginning to determine what's your range of environment. You are in clastic or carbonate. If you are in clastic, ignore these two lines. Ignore the dolomite lines, and sometimes limestone ignore it. If you have some mutation, stuff like that, you find it. And you can focus only in the sandstone and the shale. If you are in carbonate, in this case, you ignore this line, which is sandstone, and focus on these two lines. And anhydrite, in this case, you'll find it there. Okay? Okay, this is important also when you use actually the Newton density to identify the clay distributions. This has been done before using the gamma ray one total porosity, but now actually if you see the different clay distribution in oil industry, we found the three types. This is actually the pure sand. We have actually laminar, structure, and dispersion. For the laminar, actually you will see this kind of clay is already replace the grain size and fill the porosity. Most of that's why affect the porosity and the grain size, which is actually not good. For structures, it doesn't have any effect for the porosity, but affect the matrix. For dispersion, actually, it affects actually the porosity because it's already filled the pore space, but doesn't do with the grain. So the grain is matrix the same, but it's already filled the pore space, why the porosity is increased. This is what I'm looking for, which is actually relationship between neutron and bulk density to most fibers, and from these shapes we can identify how it looks like if are an eliminated sandstone or dispersed sandstone as a clay distribution. So in this case actually looks like we are already eliminated in this case, which is this kind of things affect both porosity and matrix. But when you go to here, you will see some things called dispersion. So that means I can use the density neutrons to also help me out to see the clay distribution and the deformations. This is another examples. Again, now you are expert. If you see the gamma ray, looks like, oh, it's like smooth. Actually, it's not like very have a deflections between sand and the clay. That means this already, and this actually looks like a carbonate reservoirs. Okay, and actually also you can see nitrite here also, since nitrite section looks like on carbonate. Anyway, this is looks like a carbonate reservoir, and if you make the same cross plot here for this, that means you ignore this line anymore, ignore the sand line now you're focusing this to one. By putting the limestone compatible scale, I found here actually three different things I can define. This is anhydrite, because anhydrite always you found it the density in the right of the neutron. Like actually the dolomite also, like also the shale. To differentiate between the three of them, the anhydrite will be very high value, and you look for the BEF. Dolomite also, you will see actually not high gamma ray, because dolomite sometimes doesn't have gamma ray. If you have the dolomite is something else, but here actually also you have to look at the resistivity in this case. Resistivity is not like a shale, very low value, or all of them overlay to each other. And here actually you found the limestone gas in this case. Once you plot this one, you will see what I'm talking about. This two part here, if you see here, go to the cross plot. If you see this is anhydrite. If you see this part here, looks like a dolomite. If you see this part here, it's a limestone and gas. If it is a collection of gas, later on you will see this kind of all the point here. You will actually rely on this one. By the way, whenever you plot the data, if you find any data in this line, that means they already in the water, limestone water. For example, this one limestone water, this one dolomite water, and it's actually sandstone water. If you see the data is already lie on the exactly the same. Now, for example, here this is the dolomite here and dolomite water. This is the dolomite water in this case. And the very important thing also, please look for the BEF. If you can see BEF here, this is 5. 5 means limestone. But also the doctor you said before, the 5 is dolomite also. Yes, it's a 5 dolomite, but always the sorry, the 5 is anhydrite, but always anhydrite doesn't have a porosity. You can see we have a porosity here, and of a 5 that means limestone. But here we have a 5, yes, but there's no porosity, 0, that means anhydrite. And actually the dolomite looks like a 3, which is like 3 value from the BEF here. Always look for the BEF also to get the lithology or MNN plot as well. This is very important slides. Actually, when you have a gas in the reservoir, that means all your porosity is not anymore right. It's called apparent porosity, not a true porosity. When you have a true porosity, that means you have water inside the. If you have water inside the pore space and you measure it, that means you have a right porosity. Especially if you are limestone. Okay, if you are not a limestone, it means you have to also correct for the matrix. Okay. So this actually amount of equations, different equations. For example, if you need to calculate the density from porosity from the density, this is the value here. Flow the 6 or MF so gas. If you have like you need to correct for the neutron for the gas and for ρB for the gas, this is actually the equations. All of them actually rely on the hydrogen index, and the hydrogen index of the gas, this is the equation for it, and the hydrogen index of the water, the equation for it. And this is actually the low filtrate, smart filtrate. It depends actually the 1 plus 0.73 divided by, multiplied by salinity of the water. In this case, it will be easy to find it from the mud report. Okay, guys, so this is very important. This actually it's the same equation already built in IP or built in TechLog, or you can do actually your Python script. I have my Python script already built into to see this kind of equation. It will be very easy to apply it and get it. And then actually you can see it's already coming from Schlumberger-Log interpretation principle. It is the same equation, everybody uses it, and it is the same in any software. So we'll apply these equations for dense neutron to get the dense neutron corrections, and for the same, if you remember this one here, it has a gas correction. We'll apply the same equation to get the corrections. If you go to here, apply it. Here, once I apply the correction by using the proper parameters, you can see the dense neutron limestone scale. You see here in the lateral store is overlay. That means all this data here, which was gas before, it will be actually lie on this line of the limestone. And you can see all the data which already is green here. It was before in this area, which is a gas. Now it's already in the limestone. And actually the dolomite is the same because it doesn't have any gas effect. It should be the same and the other. So that means very important to do this gas correction. Don't do any calculation with physical analysis until you get a correction for the gas and as a parameter to get the right porosity in your analysis in this case. So the conclusion actually out of this presentation, it's the porosity can be estimated from dense neutron. Dense actually porosity tool it has to be compatible scale with the neutron to get the lithology and the flow typing. I can actually know the Clay distribution from both dense and neutron. Again, you have to do environmental correction for both before doing physical analysis. Very important. Neutron and density can be run in both open hole and cast hole. If you have a BIF actually in the mud and bright, please don't look at it, don't use it. It will be crazy reading. You have to estimate it or use MN plot to get the lithology. And also the density and the neutron, both of them share depth investigation. That's why both of them run combinable together and attached to the borehole in this case. So thanks a lot for your attention, and I hope actually by this presentation I add some new value and stuff to you, and please waiting with the other upcoming presentation. I will see which one I will start with, but it will be coming within 2 weeks from now. Thanks a lot, and I hope you enjoy this kind of presentation.